Alright, so we are in AP Stat here. This is Unit 2, and we are doing a overview here of the whole unit here, Chapter 7, 8, 9, and 10. We've been hitting on scatter plots, regression lines, the correlation coefficients, how to read some of the data, and we are looking at residuals now, and looking at an influential score according to those residuals is kind of where we left off. And I believe we were taking a look at some pictures like this before. We were looking at them. If I'm moving too fast again, you got to pause these videos and write the stuff down to kind of take these notes on your own. But if I went too slow and gave you time for everything, these videos would be hours long. So anyway, here we go. Point is, if you're looking at a set of data, we're talking about what makes a point so influential, basically. And when we were talking about this the last time, we talked about the possibility of that being an outlier or that being an outlier, which is true. They probably are outliers. But this could possibly be an outlier, so could this, depending on where it's located. But it looks like because it goes in a straight line like this, it's probably not an outlier. But anyway, the point I'm getting at is what makes them so influential. All right, and we know that those are probably the outliers when we look at it. One person watched the TV for about 5 hours, we said, and then got that GPA. Another person watched for about 25 hours and got that GPA. So they probably are outliers, but the trend seems to be the more TV you watch, the lower your GPA. All right, that's just something that we were focusing on the last one. And then I said how these could possibly be an outlier as well, depending on them. But scores whose removal would shape change the regression line are called influential points, meaning if we removed these two outliers right here and they didn't exist anymore, this line would be even more straight. But now that I have to take them into account, it's kind of like, well, it's a line more like this. Whereas if I remove them, now we're talking almost a perfect straight line if we remove those outliers, which makes those points very influential to that data. An influential score may have a small residual. All right, so the residual itself could still be small but have a great effect on that regression line. It's just a possibility, but for example, consider the following scatter plot of the 6 points in a regression line. And for that right here, take a look. Consider the following scatter plot of those 6 points and this regression line, right? We have what could possibly be 2 outliers maybe, if I put those 3 there, but the point is, take a look at them. We got an outlier here which definitely looks like one, and this one some people would argue, well, is it or isn't it, right? Now look at this picture. Point is, that line right there, right? If we look at what we have, there is the original with A and B, right? With A and B, and now I'm saying, you know what, let's remove A. If I remove A, and that's no longer there, now that is my line. It's only affected by that residual. Do you follow me? If that point's not there anymore, now my new line is that. So it influenced my influential point, I guess, if you want to call it that. A was one, because look how drastically it changed that. The heavy line shows what happens when point A is removed. Now if you look at this graph, okay, look at me taking away point B, all right, and see how influential that is. So just because we take that away, you would think, oh, well, that would affect the line. Well, now it's practically the same as it was before. The heavy line shows what happens when point B is removed. And note, the regression line is greatly affected by the removal of point A, more so than point B, even though point B was farther away, right? So you look at this and say, well, point B looks like it, but just because it looks like a very big residual doesn't necessarily mean that it's going to drastically affect the line. I take that away, it's still pretty close, right? So point A is more influential because it changed it more drastically. This is true, although point A is closer to the line. That's why I gave you that example to show you what that means. Take a look at another one. Consider the effect of outliers in X, the Y, and both X and Y, the slope of the regression line, on this. So here's the original graph. I know it's a little blurry, I'm sorry, but look at that. There's the original one. All right, there's the slope. It's around 0.45, that's I can't see it. And that looks like the R is 0.866 for those that can't really read that. So outlier in X, all right, an outlier in the X direction. If I take that and add an outlier in that X direction, so boom, I added one there, right? So if I add an outlier in the X direction, it pulls the line down, right? If I add one in that X direction, it pulled it down. And notice the slope. Still a positive slope. The slope also went down, and my R also went down. okay, my correlation. Note that an outlier in the x direction can dramatically affect the slope and the correlation. So there's the original. Now if I put an outlier in the y direction, so y direction up here, right, it kind of pulled everything up. But notice that an outlier in the y direction did not affect my slope at all. Right? Slope is exactly the same. My r went down though. The correlation isn't as good as before. So notice what happened there. So as you look at this, an outlier in both directions. So I have an outlier that's also in the x and also in the y direction. All right, and you can't see that, but that is technically the same. All right, and that also is. It says an outlier in both directions will maintain the same pattern, roughly, which means the slope, same slope with a little bit of increased correlation. All right, if you take a look, that was supposed to be that the correlation is about the same, a little better correlation. But all that I'm implying is the x affects both, right, and lowers them. The y only affects the slope, or it doesn't affect the slope, it affects the correlation. But if it's in both, then it basically maintains everything, kind of makes it the same. Okay? Transformations to achieve linearity. Often a straight line pattern is not the best model for depicting a relationship between two variables. That's true. We went over this. Oftentimes a straight line isn't the best model. A clear indication of this problem is when a scatter plot shows a distinctive curved pattern. So if you're looking at a scatter plot like we saw, only like a couple examples of it, but it looks like there's a nice curved pattern to it. Another indication is when the residual shows a distinct pattern as well, rather than randomness all over the place. So, in such a case, the nonlinear model can sometimes be revealed by transforming one of both variables and then noting a linear relationship. So what I'm saying here is you take one variable, the x, or one variable, y, all right, and you alter it. So it says the nonlinear model can sometimes be revealed by transforming one of both variables and then noting a linear relationship. Do you see something that's linear? If you change the x1, the x variable, and I'll show you how to do that, is there now a linear relationship? If you change the y, is there now a linear relationship? Useful transformations often result from using log or natural log on your calculator to create new variables. So for example, considering the following years, and they correspond to that population, nice and small here. So if you want to write it down and pause the video, you got it. Okay? And the point is, let's plot the points. We press stat and edit. So we clear out our lists, even L3, you got to clear that out, clear them all, right? And plug in our points. Got them, check, they're there. All right, plug them all in. So second Y, we make sure the plots are on, right? I press enter to make sure it's on. I pick scatter plot, and in my X list and my Y list, I put L1 and L2. We've done this a ton now, right? So my plot's on. There's my scatter plot. I have my list 1 and my list 2. I go to zoom stat, and there we go. Now, some would argue it's kind of a straight line, and you know what it is. But it seems like there's a pattern. Like it seems like it kind of is curving up, doesn't it? So if I'm uncertain, I could do linear. Maybe it's not going to be linear. Maybe the next point will be even higher, so it does look like it's curving more, so it's not really as linear. This looks like a pattern to me, telling us that maybe a non-linear relationship may be more helpful, right? It kind of looks like a pattern-ish. Maybe not. We'll see. So we look at the residuals. So you go back to the main screen, and I need to redo my correlation in order to do this. Remember, if you want to get new residuals, you're going to have to go through and do a line reg to get it. You must find the regression line each time. All right, I got to find the regression line if I want to get new residuals. If I don't, it's not going to work. So if you do not, it stores the old regression line in that you did before, giving you wrong residuals, and thus you will not be able to graph this and get the correct answer. So we go to stat, calc, I go down to line reg, right? And now I have my new correlations, right? So now that I have my new correlation, first of all, I did a line reg, right? And this looks like it's about, with the data they gave me, 97% is pretty good. Like that's a 97% of the data fits, is basically what it's saying. 95% of the Y is explained by the X, is what we're basically saying. So now that we have the correlation, we can get the residuals easy. So go to our table, right? This is another way to do it. And arrow up to L3, right? Press second and stat, go down to residual, press enter. Boom, there they are, already done. The only way this is going to work for you to get those residuals is if you took the time in order to find that regression line first. So now I have my residuals, correct? And there we go. So now graph them. So you go to second Y, you make sure your plots are on, you press enter to make sure that the scatter plot's set up. But now I want L1 and L3, zoom, stat, and there. Now I can really see with my residuals, I'm looking like a pattern. Kind of looks like that parabola shape there. So again, I notice a pattern with the residuals, which guarantees me that, you know what, after seeing a pattern with the residuals as well, I was uncertain. But when I graph my residuals, I can now see that, sure enough, it does look like there's a pattern. A non-linear relationship is probably for the best. And these two things help me indicate that that would be the case. All right, it's a strong model. So here's what we do. You take these points that we had, the originals, all right, and then we change them. And here's what I'm going to do. I'm literally logging these. I went log of that number, log of that number, log of that number, and log of that, or sorry, log of this number and this one and this one. I logged all of these to get these values right here. I now have my X and my Y's, right? So now plug in your new Y values. All right, I go to edit, and in L2, I put those down, right? So now those are my new values. So take a look at my scatter plot of those. So I can press second. Y equals, make sure the plot's on, scatter plot of my L1 and L2 now. I zoom stat, and they definitely look more like a straight line to me, right? Don't they look more like a straight line? I see a pattern, but it looks pretty linear, so to double check, again, I recommend doing the residuals. So you have to find the regression line of those. So you go to stat, edit, right? I got to find the regression line first using L1 and L2, and here's what I get. And you know what? It's 1. That means it's basically 100% sure, okay? Which is pretty good. It's perfect. Perfect correlation. No need for residuals. It's literally 1. It's linear, okay? It's perfect. So our analysis is log of Y equals this, all right? Thus our analysis yields that that would be the most accurate depiction of that graph and that data. Logs can be re-expressed as exponentials. So what I would do is, because natural log is the same, I could take them both to an e, whether I natural log them and get the same answer or not. So they are the same thing for those that don't know that. So I can take them both to the e, all right, to get this, which means I can then take it through to both, mathematically move that down to the bottom. You do not have to do this at all right? You do not have to ever re-express it. I'm just showing you what you could do to basically give you that new equation. However, your goal is to log or square root or take the reciprocal or log both x and y in order to create a new linear model and or perfect correlation, or pretty close to that is your job when you're doing these. Okay, so when we come back, I'll take a look at another example.